This is a typical head capacity curve for a centrifugal compressor for different speeds, 90%, 100%, and 110%. In this section, we will devote our attention to limits of the dynamic curve, namely surge and stone wall. The first item that we will discuss will be low flow. This phenomena is known as surge. It should be pointed out immediately that surge is a system phenomena resulting from the inability of the centrifugal compressor impeller to produce the amount of head that the process system needs. Some facts concerning surge are that it is a high-speed phenomena where flow reversals can occur in less than 150 milliseconds. Pressure rapidly fluctuates, noise is generated, temperature increase can be very rapid, and mechanical damage can occur. The intensity of surge varies from application to application and is proportional to the density of the fluid. Higher pressure and higher molecular weight applications can result in greater mechanical damage. Lower density applications, like in the case of hydrogen, can cause surge damage that may not be detectable until the compressor is disassembled. The cause of surge results from low velocity in the blade or impeller passages as depicted here. It must be remembered that every dynamic blade or impeller is designed for one and only one operating point. The head is produced by the action of the blade on the flow between the blades. As the flow through the blades is reduced, the velocity between the blade passages is also reduced. As a result, the gas flow changes from laminar or smooth to turbulent, and this causes flow discontinuities. There are many causes of surge. Referring to a cross-section of an impeller and a stationary diffuser, we can see and remember from previous discussions that the gas angle of the absolute velocity of the gas exiting an impeller will reduce as the flow decreases. This was explained in details in a previous video, but is depicted here once again for a reminder. Here you have the tip speed and the relative velocity corresponding to the designed flow. If we sum these two vectors, we will get the absolute velocity r1. r1 will have a gas exit angle θ1 as depicted here. Now, if the flow reduces, the relative velocity will reduce, and then will lead to a new absolute velocity r2. r2 will have a new gas exit angle θ2. So as you can see here, as the flow decreases, the gas exit angle decreases, and θ2 is lower than θ1. The gas exits the diffuser in a logarithmic spiral fashion. This is depicted in this simplified animation. As the exit gas angle becomes less, the path the gas must follow becomes longer and eventually can turn back into the impeller, thus causing a backflow. This is one example of a flow discontinuity that limits the amount of energy or head an impeller can produce. Another example of this phenomena could occur in the impeller or blade passage itself and result in backflow. Regardless of the initial cause, the inability of a rotating blade or impeller to produce the amount of energy needed by the system will result in the gas acting on the blade or impeller rather than the blade or impeller acting on the gas. At this point, backflow can occur. If we examine a typical compressor system and look at the discharge system from the compressor discharge flange to the discharge check valve, we can see that at the point of maximum blade or impeller head production, the pipe and discharge pressure of the compressor can be thought of as an equivalent vessel, as long as the flow into this vessel is equal to the flow out. The pressure in the vessel remains constant. At the onset of surge, the compressor will no longer produce flow into the vessel, and the stored energy in this vessel now acts on the blade, resulting in a flow reversal from the vessel back toward the section of the compressor. Examining a typical compressor performance curve, we can see that as the head required increases, the operating point will move towards the surge or instability line. When the operating point intersects the surge line, a flow reversal will occur, causing the operating point to enter the negative flow region of the performance curve. This causes the vessel in our process system, seen here, to be evacuated. Once the vessel is evacuated, the system pressure observed by the compressor rapidly reduces, thus enabling the compressor to achieve a new operating point in the positive region of the performance curve at high flow, and this will cause the vessel to be filled. Once the vessel becomes filled, the operating point moves again up the compressor curve to surge, and the cycle begins anew. Remember that these cycles can occur as rapidly as 6 times per second. This action produces large amounts of energy, which are absorbed by the mechanical components of the compressor, and can result in a significant amount of temperature increase inside the compressor. Think of it this way: the gas moves back and forth in the compressor 6 times per second without being cooled, so temperature increases can be very rapid, and thermal expansion during surge can cause major damage to your compressor. This phenomena can occur most easily in axial compressors. Therefore, surge is to be avoided most in axial machines due to their ability to heat up faster than centrifugals, and also as a result of the blade configuration, which can be more readily excited than centrifugals. The high flow limit of the dynamic curve is known as choke or stone wall, and is defined as the maximum flow a given impeller can handle. We'll see this in details later on in this section. The high flow limit will be obtained when the ratio of relative inlet gas velocity to the sonic velocity of the process gas being handled is equal to 1. The high flow limit of the curve is attained when the impeller itself acts as a resistance and will not allow additional flow to be passed. We will see in a later video by referring to the relationship of the relative Mach number, which is the ratio of the inlet relative velocity to the sonic velocity of that gas at suction conditions, that higher molecular weight applications will result in a higher Mach number. Therefore, it can be stated that high molecular weight applications result in a shorter range of operation of the compressor curve. We define range of operation as the flow from surge to stone wall, as depicted here. Typical ranges for surge can vary between 60 to 80% of design flow, and carry-out range or stone wall range can vary between 110 to 130% of design flow. We'll see this in details further ahead. Surge can be a very dangerous phenomenon if allowed to continue. Damage caused by surge in any type of dynamic compressor, so whether centrifugal or axial, can render that compressor inoperable, and this for periods of times in excess of 2 months. Considering that most dynamic compressors are not spared, this can cause a significant loss of revenue. So that you are aware, typical daily product revenues for a world-class oil refinery can exceed $1 million per day. So it is extremely important to build a strong understanding of surge and know how to prevent it for flawless and reliable operations of your plant and piping system. The most common effects of surge are highlighted here. Recall first that surge is a high-speed phenomenon. Flow reversals can occur in less than 150 milliseconds. Reversal rate is 30 to 120 cycles per second. During surge, pressure rapidly fluctuates. Noise is generated, temperature increases, and mechanical damage can occur. Under surge, your unit may trip. The intensity of surge varies with the application. Of all the effects listed here, by far the most damaging is rapid temperature increase. This can cause internal rubs of the compressor at operating speed, resulting in impeller breakage, diaphragm breakage, extreme labyrinth seal wear, and possible compressor case breakage. Now take a look at the following figure. It shows the test results of an actual surge performed on a process compressor. It is the results obtained during a real surge cycle. Here, delta QC is the flow change, and delta PRC is the pressure ratio change. Notice how prior to the surge event, the pressure ratio delta PRC increases, while the compressor flow rate delta QC is decreasing. Observe that once a surge cycle is detected, the output of the controller works to open the anti-surge valve immediately. This fact is important to remember when trying to justify a field surge test to plant operations. A compressor will never be damaged by a surge test if conducted properly. As shown in this figure, process chart recorders are used and the surge system is in automatic. But the surge control line has been moved to the left of the actual surge location. The surge control line defines the set point of the surge controller, and therefore the point at which the surge control valve will open. Here you can see that as soon as the surge has started, a flow reversal has been recorded. However, thanks to the action of the controller, the anti-surge valve broke the surge cycle. The last figure that you can see here presents the characteristics of flow, pressure, and temperature during a surge. The degree of parameter change is directly proportional to the density of the gas. The higher the gas density, the greater the effect of the surge. The limits of any centrifugal compressor curve are a consequence of gas velocity in the compressor stage. These limits are the low flow limit known as surge and the high flow limit known as choke or stone wall. Surge, as we shall see in a moment, is caused by low flow turbulence, while choke or stone wall flow is caused by high velocity friction.